Hey, so let's look at how to create velocity graphs, position graphs, and a simple velocity position data table based on a particular scenario, and then we're going to abstract it into something that will work for any constant acceleration scenario. So here's the setup of this particular situation. You've got an acceleration of plus 2 meters per second, an initial velocity of plus 4 meters per second, and an initial position of 10 meters. So I've gone ahead and sketched out my velocity graph, but let's take a look at what that looks like as a column of values. So for every second on the clock, my velocity changes by 2 meters per second. Specifically, it increases. So for example, after 4 meters per second, 1 second later, I'm moving at 6 meters per second. And then another second later, I'm moving at 8. And so on. So when I plot position and velocity, I get a linear graph with a vertical intercept of 4 and a positive slope of 2. So that's the velocity graph that I previously sketched on here. So I want to generalize that for just a moment. So for any future time, let's just call that time t, any time in the future, is there a way that I can express the velocity as a function of time? In other words, by the way, what I'm asking for is the equation of this line written in function notation. Well, I see that it's a vertical intercept of an initial velocity plus the slope times the time interval, plus the time on the clock, sorry. So the slope times some interval of time. So that would be the velocity in any future moment in time is the initial plus the acceleration times that time reading on the clock. Okay, now let's look at how we can figure out the positions here. Okay, so I know this object is accelerating. And to get this next position, I need to figure out the displacement over the interval from 0 to 1 second. So on my graph, let me go out to 1 second and draw in that shape. That's a trapezoid. And like we've been doing in class, I can divide it into both a rectangle and a triangle. And I can figure out the areas of those added together. That'll be the displacement for 1 second. So the initial velocity here is 4 meters per second. The final velocity at 1 second here is 6. And this over here is 1 second. So I have all the dimensions I need in order to calculate the area underneath this shape. So first of all, 4 times 1, this is a displacement of 4 meters. And then that triangle. So this is 2 times 1, that's 2, plus a half of that. So that's going to be 1 meter. So in the first 1 second, the object's displacement is a total of 5 meters. Delta x equals 5 meters, from 0 to 1 second, 5 meters. So I move forward 5 meters from where I am right now. 10 plus 5 meters displacement puts me in a new position of 15 meters. And I can repeat that go out to 2 seconds. So this is now 1 second wide, 6 seconds tall, 6 meters. And then that triangle, same as before, also indicates a displacement of 1 meter. So now from second 1 to second 2, I travel 7 meters. 7 meters. 7 meters from where I am right now, 15 plus 7. 15 plus 7, that's 22 meters. And we're going to continue this process all the way out the velocity time graph. There's actually a little shortcut I can do here. Do you notice that this delta x is 5, this delta x is 7? I need now to continue that pattern. The next delta x will be 9, 22 plus 9, 31. Now I need a delta x of 11, 42, and so on. I can clearly see that this object is speeding up. Two ways. Well, I mean, I can just look at the velocity column and see that it's speeding up. But also, when I look at the positions over the times, I can see that my positions are changing by ever greater amounts. That's going to imply some sort of a curve that curves upwards and gets steeper as it goes. Now, my task here is to express this number. Sometimes it's convenient to go to all of this work in order to generate a column of positions, but sometimes you don't want to do all that work. You just want to get a position graph based on those initial conditions. So that's what I'm about to show you now. Can I express an object's position as a function of time without going through all that extra work? Oh, I'm sorry, time. Position as a function of time. Okay. So let's do that. This is going to be a little bit of algebra work and a little bit of graphic work here. So first of all, the way I got every number in this column is I was adding these areas. So can we express them in general terms? Absolutely. The first area that we've got going on here is an initial velocity for the time interval times an amount of time. Correction here, times a time interval. That's the area of the rectangle. And then to that, we add in the area of the triangle. So that's 1/2 the base times the height. The height, by the way, is the change in velocity. So if I want to find the new position in this line, what I'm going to do is I'm going to take my current position. Sorry, let me write this a little differently until I get to that point. So I'm going to take the position and I want to add to it the combined area of the triangle and rectangle. So let's do the triangle first. Then the rectangle. Okay. All of this together represents a new position. So it's the starting position plus the area of the triangle plus the area of the rectangle. Give me the position in the future. Let's do a little bit of algebraic manipulation to clean this up a bit. Okay, the first thing that I want to do is I want to get rid of this delta v term. It's inconvenient to always have to know the current velocity. So we want to substitute that out. I want to remind you that acceleration is delta v over delta t. Recall that, that's the slope of this graph. So if I solve this for delta v, acceleration times delta t. So we're going to make a really quick substitution into my equation. I'm going to get rid of that so I have some room. Initial plus delta v get replaced with a delta t. And then there's still a delta t here. Plus initial times time. I want to multiply this out to make it a little smoother looking. Delta t times delta t squared. I want to reorder these terms because I put them together in kind of an awkward order. This is an initial condition, this is an initial condition. Let's put them together, just reorder the order of the addition. So this is going to give you the position of the object. I know it's long looking and unwieldy, and it actually just left the bottom of the screen. There we go. All these deltas in here, we can actually take them out, because what I want to do is I want to name a time on the clock, not some time interval like between 3 and 6 seconds. So one last little step is I'm going to say position of the object, as a function of time is equal to So just a final reminder here, this is an equation that's useful for finding the position if what you know is the time on the clock and the other initial conditions. This term here represents the area of the rectangle on the velocity graph. This term here represents the area of the triangle on that graph, and this represents your starting position. This is a useful equation for populating out the position column without ever getting the velocity column. Good luck using it.